Okay, we're in section 6.4, and I was going to finish that up now, and this will be the last thing that we do for the course. So we're talking about work applications, and we've looked at lifting problems. We did problems 8 and 9, which were related to lifting a rope or chain. Lifting water is also a variable force problem. So I don't really care for how the book presents the information for this topic. So I have a kind of just a list of steps that I think maybe make the setup easier. So I would encourage you to maybe consider using this option here. Here's the steps for finding the work done to lift fluid from a tank. Step 1, draw a picture with the coordinate axes included that will represent the problem and choose a convenient origin. Make the y-axis in the vertical direction as you normally would. Step 2, find the cross-sectional area, which we'll call A of y, and that'll be for the horizontal slices. Step 3, let the level of where the fluid is to be lifted be at y equal h. Then the distance that each slice at level y must be lifted is h minus y. And then step 4, let the fluid that is to be lifted range from y equal a to y equal b. Then the work done to lift the fluid is represented by this integral formula that you see. This is a formula in terms of y. Okay. Rho is a Greek letter, is the mass density of the fluid. Okay. Here's another measurement note. In the SI metric system, the mass density of water is rho equals 1,000 kilograms per cubic meter. And in the U.S. customary system, we use the weight density as opposed to the mass density. And the weight density of water is represented by delta, which is 62.5 pounds per cubic foot. Okay, so just like all these other problems, we'd want to know early on which system we're in, if it's the SI metric system or the U.S. customary system. We'll know that early on by the unit measurements that are given here. So let's take a look at problem 10, where it says an open tank has the shape of a right circular cone and it is full of water. The tank is 8 feet across the top and then 6 feet high. How much work is done in emptying the tank by part A, pumping the water over the top edge, and then part B, pumping the water to a height of 4 feet above the top of the tank? Okay, so I've drawn a picture. Again, step 1 is to draw a picture and choose a convenient origin. Okay, so I've done that. I've centered this right at the origin. And we've got a cone-shaped tank, and the tank is 8 feet across up at the top, so I'll go from -4 to 4 on the x-axis, and it is 6 feet high on the y-axis. Okay, how much work is done in emptying the tank by pumping the water over the top edge? Well, so here's the integral formula that I'll need to be working with. And of course, I'm in the U.S. metric system here, U.S. customary system, because of the units that are given there in feet, not meters. And the weight density of water is 62.5 pounds per cubic foot. Okay, so that's going to be a constant that would just go outside of my integral. That weight density already figures in the acceleration due to gravity. Okay, so I won't need to do that. But inside the integral, I'll need a function a of y that represents the area of the horizontal slices. Okay, so as the water is being pumped out, discs that would be a circular shape are being removed or lifted from the tank. Okay, so I'll need to have just a general formula of the area of each one of these circles. Now, of course, the circles are going to be smaller in size because of the shape of the tank here. But in this picture, all right, I've I'm looking at the line that is going from 0, 0 to 4, 6. Okay, I'm going up 6 and to the right 4, or that'd be the same as going up 3 and to the right 2. So the equation of that line would be y equal 3 halves x. If I solve for x, x would be equal to 2/3 y. Now x would be the distance from the y-axis to the right side of the tank. That would also be the radius of the circle that is being removed from the tank. Okay, now I need a formula for the area of the circle that's being lifted from the tank. Area of any circle is pi times the radius squared. Now, I mentioned everything about my integral has to be in terms of y. Okay, that was in the formula there. And so a of y would be pi times the radius squared. It would be pi times the x is the radius, like I said. So in terms of y, that'd be 2/3 y. Or pi times 2/3 y, the quantity squared, would be just the general area of a circle that's being lifted from the tank. Now, h is the level where the fluid that is to be lifted is what we're calling h. Okay, and so the distance that each slice has to travel is h minus y units. Okay, so in this problem, h is 6. Each circle is going to be lifted a distance of 6 minus y feet. Okay, so the bounds, and I'm going to completely empty the tank here. The bounds are going to be going from 0 to 6. And the leftover then in the integral, I'm going to want 6 minus y. And then be sure to have dy at the end. Okay, so if y is 0, you've got all 6 feet of water in the tank. If y is 6, 6 minus 6 is 0, and at that point the tank would be completely empty. So now we're all set up, and now it's just a matter of finding the value of this integral. Well, 2/3 squared is 4/9 times pi. You can bring that in front of the integral, and then I'm going to distribute the y squared into these two terms, and then I can take the antiderivative. Plug in the bounds. Of course, when I plug in 0, both these terms are going to be 0. So when I plug in 6 and then simplify, I get 3,000 pi, or that would be roughly 9,424.8 foot-pounds would be the unit measure that I'd have there at the end. Okay, now how about part B? How much work is done in emptying the tank by pumping the water to a height of 4 feet above the tank? So the only adjustment in what you saw I did in part A would be the h value. H would be 10 if the water is going to be lifted to a spot 4 feet above the height of the tank. Everything else would be the same. Okay, my bounds, I'm going 0 to 6, would indicate that the tank is completely empty. You got 6 feet of water there. And we're going to empty the tank. So again, I've pulled the constant 4/9 pi out front, distributed y squared into the two terms, taken the antiderivative, and then I plug in my bounds, and I'm getting 11,000 pi foot-pounds is the exact answer, or roughly 34,557.5 foot-pounds if I go nearest one digit. Okay, let's take a look at problem 11, the last one here. A cattle trough is 10 meters long and it is full of water. The trough has a trapezoidal cross-section with the height of 1 meter and the horizontal sides of widths 1/2 meter and 1 meter. How much work is done in pumping the water out over the top of the edge in order to empty part A, the entire tank, and then we'll empty part B, half the tank. All right, so again, I've drawn a picture. That's step 1. Choose a convenient origin there. And so I've positioned this trapezoid so that it's symmetric about the y-axis, and the bottom of the trapezoid is right on the x-axis. The sides of the trapezoid, the horizontal sides, are 1 meter and 1/2 meter. Okay, so if I'm 1 meter up at the top, I'd want to go from negative 1/2 to 1/2 on the x-axis to go 1 meter across. And then it's a 1/2 meter at the bottom. So here's negative 1/4 to 1/4, or at this point here that I've got labeled would be 1/4 0. The trapezoid has a height of 1 meter. That'd be the height of the trough there. So this point here that I've got marked would be 1/2 1. Now, as sections are being lifted from the tank, they would take on the shape of a rectangle, right? The trough is 10 meters long, so the length of every one of those rectangles would be 10 meters. The width is going to vary though, right? I'll be removing larger rectangles initially, and then as the tank is being emptied, smaller rectangles are being lifted once I get towards the bottom there. So I'll need just a general formula for the area of each one of those rectangles. Well, let me work with this line segment here passing through these 2 points, 140 and 1/2 1. And let me get the equation of that line. The slope of the line, change in y over change in x, would be 1 minus 0 divided by 1/2 minus 1/4, that'd be 4. The equation in slope-intercept form would be y equals 4x minus 1. So if I solve this for x, add 1 divided by 4, x is equal to 1/4 the quantity y plus 1. Now x is the distance from the y-axis to the right side of the trough. 2x would be the total distance across the trough. And that's what I want, since that would give me the width of the rectangle. Again, the length is 10 meters. So the width would be 2x. But since everything has to be in terms of y, x in terms of y is 1/4 times the quantity y plus 1. Okay, when you multiply that by 20, you get 5 times the quantity y plus 1. So that's going to go in the integral here, representing a of y. Now, also, I noticed that I'm in the SI metric system because meters are represented here for the measurements. So my answer is going to be in terms of joules when I calculate the work done to empty the tank. Now, also because I'm in the SI metric system, the mass density of water is 1,000 kilograms per cubic meter, and the acceleration due to gravity is 9.8 meters per square second. Okay, so I've got those constants in front. That's rho times g times the integral going from 0 to 1. So the fluid level here is ranging from 0 to 1 on the y-axis. And a of y, we've already got that. H would be 1, right? H is the level to where the fluid is to be lifted. Okay, so each rectangle is going to have to travel a distance of 1 minus y meters. So if h is 0, then you have the tank is completely full at that point. If h is if y is 1, if y is 0, then the tank is completely full. If y is 1, 1 minus 1 is 0, and at that point the tank would be completely empty. Stick a dy at the end. Okay, and here'd be my setup then, representing the problem. And now I'd want to simplify. So if we take 1,000 times 9.8, that would be 9,800, times 5 would be 49,000. I'm going to go ahead and FOIL out y plus 1 times 1 minus y. That'd be 1 minus y squared inside the integral. And then I can take the antiderivative. Y minus 1/3 y cubed, okay, times 49,000. We're evaluating that from 0 to 1. And when I plug in the bounds, Okay, 1 minus 1/3 is 2/3 times 49,000 would be 32,666.6 repeated joules. Okay, and that would be the work done in emptying the tank. Part B, how much work is done in pumping the tank, the water out over the top of the edge in order to empty half of the tank? Now, obviously, in Part B, you're emptying the top half. Now, that's going to be important for our setup, okay? And emptying the bottom half doesn't make sense if you got water still sitting on the top half, right? But we need to make sure that our setup, is fitting to the situation here. Now, the only change from what we had set up before is going to be the bounds on the integral. It says the fluid level that is to be lifted is going to range from y equal a to y equal b. Well, I'm removing the top half of what we see in the tank. So I'm going to want to go from 1/2 to 1. Everything else is going to stay the same. Now, notice that we do not integrate from 0 to 1/2. Okay, some students might tend to want to do that. They put 0 to 1/2 because, hey, we're going to empty half the tank, right? So it's got to be 0 to 1/2. It's not going to be 0 to 1/2 because this would mean that the trough is only half full. It's not. It's completely full. But with bounds that are going from 0 to 1/2, that would indicate that it's only half full, and the water would be traveling a 1/2 meter up to the top in order to be empty. We don't have that going on, right? You can kind of relate that to what we did there in the previous step where the water has to travel an additional 4 feet. Okay, I don't have any situation like that happening here. Okay, so the bounds are going to be going from 1/2 to 1, and like I said, that's the only change compared to what it was in Part A. The antiderivative would be the same. I'm just plugging in different bounds here. So when I plug in the bounds and then simplify, I'm getting 10,208.3 repeated joules. Okay, now in Part C, explain why the answer in Part A is not twice the answer in Part B. So how come this answer here in Part A is not just twice the number that you see there? Well, the bottom half had to be pumped a greater distance than the top half. By the way, the shape of the tank is somewhat relevant to what we're doing, but if I had a rectangular face, there would still be more work in pumping the bottom half than the top half, because the discs would have to travel larger distances in the bottom half. So more work would have to be done in lifting those out of the tank. Okay, and of course we see that here. Even though these rectangles are going to be smaller in area, they have to travel longer distances compared to these ones up at the top, okay, that are just lifted right out and you're done. So more work is going to be done in emptying the bottom half compared to the top half. All right, so that's it then. We are now done with what I wanted to cover in Chapter 6. There is one more section which you can read about if you'd like, Section 6.5. It's not an overly critical thing to know, in my opinion. Moving on. So at this point, like I said, we're done, and your last homework assignment is on page 458. Be sure to look at the odd-numbered problems for me, and also problem 34 that I got there.